In the very beginning of the universe, there was no water at all. Not a single drop. About 13.8 billion years ago, the universe began with a huge event known as the Big Bang. This was not an explosion like a bomb, but a rapid expansion of space itself. Everything was extremely hot, bright, and packed tightly together. At that time, the universe was too hot for atoms, too wild for chemistry, and far too violent for something gentle like water to exist. As the universe expanded and cooled, the first simple particles slowly combined. After a few minutes, the very first elements were formed. These elements were hydrogen and helium, with tiny traces of lithium. Hydrogen was everywhere. Helium was also common. But oxygen, which is essential for water, did not exist yet. This is very important to understand. Without oxygen, water cannot form. So even though hydrogen was abundant, the universe was still completely dry. For millions of years after the Big Bang, the universe was dark and quiet. There were no stars, no planets, no galaxies, just huge clouds of hydrogen and helium gas floating through space. Over time, gravity began pulling these gases together. Wherever the gas became dense enough, it collapsed under its own weight, and the first stars were born. These stars were massive, bright, and very different from the stars we see today. Inside stars, something extraordinary happens. Stars are like giant nuclear factories. In their cores, extreme heat and pressure force atoms to combine in a process called nuclear fusion. At first, stars fuse hydrogen into helium. This releases enormous energy and makes stars shine. But in very large stars, fusion does not stop there. As hydrogen runs out, the star begins fusing helium into heavier elements such as carbon, nitrogen, and oxygen. This is how oxygen was created for the first time in the universe. Oxygen did not come from the Big Bang. It was forged inside stars over millions of years. When these massive stars reached the end of their lives, they exploded in powerful events called supernovae. These explosions were so intense that they scattered the elements made inside the stars into space. Oxygen, carbon, nitrogen, and many other elements were thrown across the universe, enriching the surrounding gas clouds. Now, for the first time in cosmic history, the universe had both hydrogen and oxygen in the same regions of space. But water still did not immediately appear everywhere. Space is cold and empty, and atoms do not easily combine on their own. Something special was needed to help hydrogen and oxygen meet and stick together. That helper was cosmic dust. Cosmic dust sounds small, but it plays a huge role. Dust grains are tiny solid particles made of carbon, silicon, and other heavy elements. They float inside clouds of gas in space. These dust grains act like meeting places. Hydrogen atoms stick to the surface of dust grains, move around, and sometimes meet other hydrogen atoms. Oxygen atoms also land on these dust grains. When hydrogen and oxygen meet on a dust grain, they can react and form water molecules. This process mostly happens in cold, dark regions of space called molecular clouds. These clouds are dense, cold, and protected from strong radiation that could break molecules apart. Inside these clouds, water begins to form slowly, molecule by molecule. Some of this water becomes gas, and some of it freezes into ice, coating dust grains like frost. So water first formed in space long before planets existed. It formed quietly in dark clouds between the stars. Over time, gravity caused parts of these molecular clouds to collapse again, forming new generations of stars and surrounding disks of gas and dust. These disks are called protoplanetary disks. Inside these disks, planets begin to form. Dust grains coated with ice collide, stick together, and grow larger and larger. Eventually, they form asteroids, comets, and planetary bodies. Comets are especially important in the story of water. Comets are often called dirty snowballs because they are made of rock, dust, and large amounts of ice, including water ice. These comets formed in the cold outer regions of young solar systems, where water ice could survive. When our own solar system formed about 4.6 billion years ago, the Sun ignited at the center, surrounded by a disk of gas and dust. Close to the Sun, it was too hot for water ice to survive, so the inner planets like Earth formed mostly dry. Farther away, beyond what is called the frost line, water ice was stable, and comets and icy bodies formed in large numbers. Early Earth was extremely hot due to constant collisions and volcanic activity. Any water present at first would have evaporated into space. But as Earth cooled, something amazing happened. Asteroids and comets from the outer solar system began crashing into Earth. Many of these objects contained water ice. When they hit Earth, their ice melted or vaporized and then cooled, adding water to Earth's surface. At the same time, Earth itself released water from its interior. Volcanoes released steam and gases trapped inside the planet. As the planet cooled further, this steam condensed into liquid water and fell as rain. This rain continued for millions of years, slowly filling low areas and forming the first oceans. So Earth's water came from two main sources: water delivered from space by asteroids and comets, and water released from Earth's own interior. Both sources trace their origins back to water molecules that formed in space long before Earth existed. What makes this story even more incredible is that water is not rare in the universe. Astronomers have found water vapor and ice in many places. In distant galaxies, around newborn stars, inside molecular clouds, on comets, on moons, and even in the atmospheres of some exoplanets. This means the basic ingredients for life may exist in many parts of the universe. Water is special because of its unique properties. It stays liquid over a wide range of temperatures, it dissolves many substances, and it helps complex chemistry happen. These properties make it essential for life as we know it. That is why scientists searching for life beyond Earth always look for signs of water. In a beautiful way, every glass of water you drink has a cosmic history. The hydrogen in it was created during the Big Bang itself. The oxygen in it was forged inside ancient stars that lived and died long before our sun was born. Those atoms traveled through space, joined together on tiny dust grains, became part of comets or rocks, and finally arrived on Earth. After billions of years, they became part of oceans, rivers, clouds, plants, animals, and you. So water is not just something from Earth. It is a gift from the universe. It connects us to the first moments of creation and to stars that no longer exist. When you look at water this way, it is no longer ordinary, it is cosmic, ancient, and deeply meaningful. Water existed in the universe before the first galaxies did. That sentence alone should stop you in your tracks. A team led by astrophysicist Daniel Whalen at the University of Portsmouth has shown through state-of-the-art simulations that water molecules began forming just 100 to 200 million years after the Big Bang, billions of years earlier than anyone expected. The key? The deaths of the very first stars. These ancient giants, called population 3 stars, were up to 300 times the mass of our Sun. They burned through their fuel fast and died in colossal supernova explosions, forging oxygen in the process. Before them, the universe had no oxygen at all, just hydrogen, helium, and traces of lithium. Once those supernovae scattered oxygen into the surrounding gas, it combined with the abundant hydrogen to form water, sometimes within just 3 million years of the explosion. What happened next is just as remarkable. Gravity pulled this water-enriched gas into dense clumps, the same clumps that would become the birthplaces of second-generation stars and, potentially, the first rocky planets. This means habitable worlds with water could have started forming at cosmic dawn, long before the Milky Way even existed. Future telescopes like the Square Kilometre Array may soon be able to detect the faint signatures of this primordial water across the early universe.